welcome to DS Tech. In today's class, we are going to see about transformer. In this topic, we are going to see about what is transformer, what are the classifications, what are their working principles. Like this, in today's session, we are going to see. First of all, transformer is a static device. Transformer is a static device which is used to transform the electrical power from one circuit to another circuit without any deviations in the frequency. Okay, so with the at the same amount of frequency, transformer can able to transfer the electric power from one circuit to another circuit. So it basically operates on the principles of mutual inductance. The principle behind transformer is the generation of electromotive force, which is none other than mutual inductance. So next, in the classifications of transformer, we are going to see there are this classification based on their construction, voltage output, and then duty they perform on the applications. So based on the constructions, there are three types like core type transformer, shell type transformer, and berry type transformer. And based on the voltage output, there are three like step down transformer, step up transformer, and auto transformer. And then the third one is from the duty they perform, there are three like current transformer, potential transformer, and power transformer. And then based on the applications, there are three types like welding transformer, furnace transformer, and ratio transformer. And based on the supply we are given, there are three like single phase and three phase transformer. Based on the cooling type, there are two, dry type transformer and oil imposed transformer. These are all the classification of transformer based on their construction. There are six constructions like uh, uh, there are six constructions like their constructions. There are six classifications based on their constructions, the way of applying voltage, the duty they perform, the applications they are used, based on the input which they work, and then the cooling. Based on the six categories, we can classify the transformer. Then the next topic is transformer construction. See, this is the construction of the transformer. In the construction of the transformer, we already know that in transformer there are two winding. One is a primary winding and another one is a secondary winding. The general working of transformer is that when I am applying the AC signal, the number of windings with the help of the applied AC signal, there is a flux creation in the same winding, in the same primary windings, means it is called self inductions, or due to the applications of AC signal in the secondary winding, there is a flux creation in the secondary winding itself, means it is called a self inductance. So or else with the help of the primary winding and the voltage applied in the AC signal, and due to the number of turns in the AC signals, if there is a creation of flux in the secondary winding, means it is called mutual inductance. That is, the primary winding is mutually creating a flux on the secondary winding. Similarly, the secondary winding, with the help of the applied voltage at the secondary winding and the number of turns in the secondary winding, it is able to generate a electromotive force or flux in the primary winding. It is also called a mutual inductance. So same like that, in this construction we can able to see there is a AC signal which is the input that we are applying to the transformer, and then there is a two windings like primary winding and the secondary winding, each are having n number of turns, where the number of turns in the primary winding is denoted as n1 and the number of windings in the secondary winding is denoted as n2. With the help of the voltage, the current flow in the primary winding is denoted as E1 and the current flow in the secondary winding is denoted as E2. And then the overall connecting part of the primary and secondary winding is called as the core. With the help of the voltage and number of turns and the field, there is a creation of flux. Maybe it can be self-indexed or mutual indexed. Okay, this is the construction of the transformer. So in the construction of the, we can see the detailed version of construction of transformer. Means for a single phase transformer, there is a primary winding, where the winding which is connected to the AC supply is called primary winding, and the secondary winding is where the secondary winding is connected to the load is called secondary winding. And then the third one is transformer core. The two windings in the transformers are coupled over a core, where it is a magnetic core which is made up of thin silicon laminations, where the lamination is responsible for continuous magnetic path within a minimum of air gap. Okay, so the core is made up of silicon steel, which is used to reduce hysteresis loss, and the laminations are used to reduce eddy current loss. Here the magnetic core and laminations are playing a major role in reducing the losses. The laminations are and then the laminations are insulated one over another. It is like uh, slotted by slot. So one over another is by a oxide layer, layer by layer, or by a core light coat of core plate. So and then the thickness of the lamination is varies from 0.35 mm for a frequency of 15 Hz to 0.5 mm for a frequency of 25 Hz. If the frequency is 25 Hz means, if a frequency is 25 Hz means the is the thickness of the lamination is high, and if the frequency is 50 Hz, the thickness of the lamination is low. Then based on the type of transformer construction, there are two, right? Like one is a core type, another one is a shell type. In core type transformer, the same transformer construction that we already see, and this is the core type transformer. Here it is look like a laminated sheet. We can see here. Here the windings are surrounded by the steel core, where it is in rectangular shape and the coils are cylindrically circulated. There are two limbs in the core type transformer, which is holding the windings in each of the limbs, and then the windings are made up of two L-type stampings. The core type transformer has only one path for the magnetic flux. The effective core area of the transformer also can be reduced by the use of laminations or the insulations. And then in order to minimize the air gap, there is a joints between the strips of the layer which are stackly alternated. The second one is shell type alternator. In this, the structure is look like a steel core which surrounds the major part of the winding. There are three limbs like HVLV. The primary and secondary windings are placed in the central limb. The low voltage and high voltage windings are wound over the central limb and are sandwiched. It looks like a book type. The windings occupy the entire space in both windows of the core. The entire flux passes through the central limb but divides the outside lamp. And then when we go with the working principles of transformer, a transformer operates on the principles of mutual inductance, where the mutual inductance is acting between two inductively coupled coils. We know that if it is a coil, it is only a inductance. So it consists of two windings like primary winding and secondary winding, where both windings are coupled by magnetic induction. Here the primary winding is energized by a sinusoidal voltage, and the secondary winding is loaded by the or energized by the load. Here the alternating current in the primary winding sets an alternating flux in the core, and the secondary winding is in the winding also creates a flux, where the EMFs are induced in the two windings. The EMF induced in the secondary winding drives current through the load to the winding. Here the energy is transferred from primary circuit to secondary circuit with the medium of magnetic field. For an ideal transformer, then we can see the ideal transformer, where the ideal transformer is the one which following the parameters like no winding resistance, no magnetic leakage, no core loss, and no copper loss. This is or the conditions for ideal transformer. The same diagram we are looking here, but there is no load here in the ideal transformer. In ideal transformer, there is no any point of core losses, any type of leakages or present. Then consider an ideal transformer whose primary is connected to the sinusoidal alternating voltage V1 and the secondary is considered as open, because in the normal transformer we are having a load, but in the ideal transformer there is no load. The secondary winding is just open circuited. Whenever a current flows through the primary winding, then the current is called magnetizing current, because the current is directed or are controlled by the magnetic field. Okay, the primary winding draws a small magnetizing current that is denoted as Im, which lags behind the voltage V1 by 90 degree, and this alternating current Im produces an alternating flux pi, which is in phase with the Im. We have to keep in mind that the voltage is lags the current Im lags the voltage by 90 degree, and the Im produces a flux pi which is in phase with the flux created is in phase with Im, and the voltage was only lagged by the current by 90 degree. The alternating flux pi linkage both the winding and induces EMF E1 in the primary and induces an EMF E2 in the secondary. This is the Phasor diagram of the ideal transformer, where we can see here the voltage V1 and V2 is vertically present and the flux is horizontally denoted. Here the magnetizing current is looking towards pi direction, and the electric field is looking towards V voltage direction. Flux pi has taken as the reference phasor. The primary EMF E1 and the secondary EMF E2 lag behind the flux by 90 degree. Note that the E1 and E2 are in phase and E1 is equal and opposite to V1. Then we move on to the EMF equation of a transformer, and you can see the waveform of the flux, where we are taking the period as t equal to 1 by f, where the time is equal to inversely proportional to frequency. Here the n1 denotes the number of turns in the primary winding, n2 denotes the number of turns in the secondary winding, and pi m is the maximum flux in the core. We know that the pi is the flux and pi m is the maximum flux in the core, which is measured in Weber. So while we are considering pi m is equal to Bm into A, where Bm is the maximum flux density and A is the area of the core. Okay, then F is the frequency of AC input, which is measured in hertz. So from the figure we can state that the average rate of change of flux is equal to pi m. From the waveform of the flux we can denote it as pi m divided by 1 by 4 F. Then according to Faraday's law of electromagnetic induction, average value of EMF per turn is equal to 4F pi m into V. And for a sinusoidal waveform, the form factor is equal to RMS value divided by average value, which is equal to 1.11. So then, meanwhile, the RMS value is equal to form factor into average value, and then the average value is equal to form factor RMS value divided by form factor. The RMS value of EMF per turn is 1.11 into 4 pi fm. Therefore, the RMS value of EMF induced in primary winding is equal to 4.44 F Bm A N1 volt, where it is replaced by pi m. Similarly, the same for E2, where the number of turns is only replaced as N2. Then we go with the voltage transformation ratio. The transformation ratio is nothing but it is the difference between secondary voltage and the primary voltage, where it is denoted by K, where the expression is standard as E2 divided by E1 equal to N2 divided by N1 is equal to K, where whenever the number of turns in the secondary winding is greater than the number of windings in the primary, then the voltage transformer ratio is greater than 1, which is called a step up transformer. And for step down transformer, the number of turns in the primary winding is, and the number of windings in the secondary winding, while comparing, the number of windings in secondary winding is less than number of windings in the primary winding, where K is also less than 1. It is called a step down transformer. For step up transformer, the turns in the primary winding is low, secondary winding is high, so that the voltage transformation ratio is also greater than 1. For step down transformer, the number of turns in primary winding is high and the number of windings in the secondary winding is low, so that the voltage transformation ratio is less than 1. Okay, then the voltage transformer ratio for an ideal transformer means we know that in ideal transformer E1 is equal to E2, where V1 is also equal to V2. So we can write it as input is equal to output, right? So V1 I1 equal to V2 I2, or else E1 I1 equal to E2 I2. By taking the equation into consideration, we can take voltage ratio as E2 divided by E1, which is equal to K, and current ratio I2 divided by I1, which is equal to 1 by K. Then we go on with the losses in the transformer. In transformer, there is no moving part or rotating parts like in DC generator or DC motor, and there is no friction or windage losses. The losses occurs in the transformer are majorly due to core loss. One is core loss, another one is copper loss. Here the core loss is also called as iron loss. In core loss there are two, like hysteresis loss and eddy current loss, where hysteresis loss is reduced by the use of lamination and eddy current loss is used by the use of magnetic core, because the core flux remains constant for all loads and the core losses also remains constant. So for hysteresis loss, WH is equal to neta B max 1.6 FV per watts, and in eddy current it is denoted by BB squared F squared D squared watt. The hysteresis loss is minimized by the use of high steel of silicon content for the core, and eddy current loss is minimized by using the laminations of the core. And then we see the copper loss. This loss is due to the ohmic resistance which is present in the transformer winding. So the total copper loss is due to, we know that V equal to I squared R, right? So the copper loss is due to I1 squared by R1 plus I2 squared R2 equal to I1 squared R1 equal to I2 squared R2, where I1 and I2 are the primary and secondary circuit, R1 and R2 are the primary and secondary winding resistance. Next, in the efficiency of the transformer, we know that the efficiency is nothing but it is the difference between, it is the ratio of output power divided by input power, where neta is equal to output power divided by input power into 100, where input power is denoted by output power plus the losses occurred equal to output power divided by output power plus, in losses there are two, like copper loss and iron loss. So output power equal to output power plus copper loss plus iron loss, where neta is equal to input power minus losses divided by input power, which is equal to 1 minus losses divided by input power. So the condition for maximum efficiency is the copper loss should be equal to iron loss. And about the efficiency, the all the efficiency of the transformer is equal to the output energy and the input energy, the ratio between the output energy and the input energy over 24-hour period. So the all time efficiency is denoted by output power in kilowatt hour divided by input power in kilowatt hour for 24 hours. The efficiency is always should be less than the commercial efficiency of the transformer. Okay, in today's class about the transformer, we have seen what is transformer, what are the classifications of transformer, and then what is the construction of the transformer, what are the working principles of the transformer, and then the ideal transformer, voltage transformation ratio, efficiency, alt efficiency. These are all the things we have discussed today. So if is there any doubt, you can refer here. Until then, do share and subscribe. Thanks for watching.